remind him about the time?
Well,
It's half an hour, but
maybe just before the 5 minutes.
You negotiating?
Okay. Tomo is fine.
Tomo,
yes.
okay.
I usually use just anything.
Okay, so we continue now with our first contributed talk, which will be by Tomoyuki Yamakami, if I said that correctly.
Yeah, that's right.
Speaking on logical expressibility of Syntactic NL, complementarity and maximization.
Thank you very much. Well, I'm pretty much interested in the computation. So this is a talk, work, to try to understand the computation, computability in terms of logic. Okay, so this is an outline of my talk. This is all about a complex class called SNL, Syntactic NL. So this is defined in terms of the second order sentences, but particular kind. Okay, and I'm going to discuss the computational complexity of the SNL. This is the complexity class, right? And also I'll talk about the some variants. But don't worry, I'm going to define those classes shortly. And I'm going to show some important properties, including the upper and the lower bounds of the complexity, computational complexity of SNL. Okay. So I start with a brief historical background. So some time ago, Papa Dimitriou, Yamakakis, and Federer and WoLLIC, they independently introduced the subclass of NP. NP is a non-deterministic polynomial time. They call it an SNP, and that is actually defined in terms of logic, second order logical sentence of this particular form. So the first one is the second order existential quantifier, that followed by the universal, first order universal quantifier. So this one is the quantifier free ponder. So this particular form. Okay, very simple, right? And SNP comes in between NP and NP. And also the Papa Dimitriou and Yamakakis, and they also introduced maximization, optimization version of the SNL called the Max SNP, right? And they also proved that all problems belong to the Max SNP. This problem is actually approximately solvable in a polynomial time with constant approximation ratio. So that's pretty nice. But we do not know all that maximization problem in NP satisfy the same kind of condition.
Did you mean a maximization version of SNP?
Okay. Yes.
In the one above, Papa Dimitriou Yamakakis.
Yeah, that's right. They introduced it. I think they introduced the Max SNP.
It's just an SNL. I think you mean SNL. I think next to
There's a typo in there.
Typo, okay.
Just a typo, just a typo, I think.
Which one is?
SNL. You wrote SNL, but it should be SNP.
Oh, sorry. Yeah, that's right. So yeah, that's the complex class I'm going to talk about. Okay, so this is just a historical background. Yeah, that's right. That's SNP, of course. Yeah. So so this is the complex class I'm pretty much interested in. Non-deterministic log space complexity class. This class is the collection of the decision problems determined by the non-deterministic Turing machine using log space. NL comes in between L and P. So this is actually the lower complexity class if you think about the P. And NL satisfies a very distinctive property called the NL is closed under complementation. So this property is not known for NP. So this fact show that the NL looks quite different from NP. Now, the NL is the main target of this talk.
Hey, but why would it look like NP? It's more like an analog of P space, no?
Well, the P space is really, really far away, right? And if you just draw the picture like this one, right? So then I'm just, well, I think that a lot of people, a lot of researchers are more focused on the NP rather than the P space somehow. Yeah, well, probably this is not the right answer to your question, but okay. The the class complexity class in NL contains a very interesting problems. For example, the two satisfiability problem, 2SAT. Okay. If you take 3SAT, 4SAT, and any K-SAT, those problems are actually NP complete, right? But if you look at it in the 2SAT, for example, 2SAT had this form, right? Each the clause has at most 2 literals. Okay. This problem is proven to be NL complete under large space manual reductions. Okay. So Yamakami studied the variant of the 2SAT, the problem 2SAT, the 2SAT K. The 2SAT K is the restriction of the 2SAT to the formula. Each variable appears at most K times in the form of the literals. For example, this is an example here. X2 appeared at most 3 times. Okay. So 2SAT K is also NL complete, right? But we do not know whether the 2SAT K is solvable using log space. Because then if this is true, then we prove that L equals NL. Right? So the complexity of the 2SAT is given like this one here. So the 2SAT with n variables and n clauses is solvable in the polynomial time using at most this amount of space. So this is the n to the 1 minus c over square root of log n. It's not constant. So still we do not know whether this point, this this formula can be reduced to just a constant in between 0 and 1. 1 is not equal. So in this term is called sublinear because 1 is not included, so that we only have an n to the epsilon which is smaller than 1. Right? Okay. Now here is a very interesting hypothesis called the working hypothesis called the linear space hypothesis, LSH. So LSH states that there is no deterministic algorithm that solves the 2SAT 3 in time polynomial and this amount of space. So this is the number of the variable that appeared in the formula of the 2SAT 3, right, to the epsilon. So this is actually sublinear in terms of the number of the variables. So this is a statement that is not even proven yet. But this is if this is true, then L and NL are separated, and also the log DCFL is different from log CFL. So this is the log manually. Okay, so this is the closure of the CFL under log space manual reduction, and this is the closure of the DCFL, deterministic CFL, under log space reduction. Okay, so this is we do not know whether this is true or not, but if this is true, then we have a very interesting consequences. All right. Now I'm going to explain about the SNL. Right. So this is a log space analog of SNP. Okay. Now, the Yamakami introduced this syntactic NL in 2017, some time ago, and also he introduced the subclass of the SNL called the SNL Omega. Okay, I'll just briefly give the definition of the SNL. So this is based on the logical system. So the vocabulary consists of the predicate symbols of the particularity and the constant symbols, 0 and n. And also we have other symbols, right? Now this notation states the set of integers from 1 up to n. And this one is a particular function symbol showing the successor. And this is the predecessor. Okay. In the variables, we have two different kinds. And first order variable, we use the lowercase alphabet. And second order variables, I tend to use the capital, the upper case letters. And we use the standard logical connectives. And atomic formulas are predicate symbols, and the second order comes from the second order variables. And also equality and inequality for the first order constant and variables. Okay, we will use two different kind of quantifier. The first order universal quantifier and the second order existential quantifiers. And when we use the second order quantifier, I use particular kind of form, so which is called the functional existential quantifier. So this notation is the abbreviation of this kind. And so this basically says that P is treated as a function. So P takes several argument classes. The first one is considered to be the input. The rest, well, even though there are many, but you just think about it, the series or tuples, right? That is the outcome of this function. And those statements guarantee that P behaves like a function, so that for any input, the output has to be defined, and also the output has to be unique. Okay, now the SNL formula has this form. Okay, we have several functional quantifiers and universal quantifiers over there, and we have some conjunction of quantifier-free statement formulas. And phi sub j have to satisfy these two conditions. And first one, the phi sub j contains those kind of things. So we do not allow a whole bunch of application of the successive functions. Each have to be finished at some constant a. Right? And also, the phi sub j can be written logically equivalent to the form of finite disjunctions, each of which satisfy the condition like this one. There are at most two conjuncts containing second order variables, and each of them must have this particular form. Right? So this guarantees that whole stuff is kind of nicely fit into the log space constraint. So the sentence means the formula does not have the free variable. Okay, so semantics of this formula is the following things. And we have the interpretation of the predicate and the constant symbols, and we have the interpretation of the variables. And sentence phi is called the syntactically expressed A. A is the language or decision problem, right? For any instance given to A, we have a corresponding relational structure and domain structure here. That's completely characterized, whether an X belongs to A or X does not belong to A. Okay? Just simply looking at whether phi is true or false. Right? And SNL is a collection of languages or decision problems that is characterized by this phi, expressed by this phi. All right. Now, this is just a simple example. The problem with two colors. So this is the given undirected graph. We simply paint the vertices into two colors. Okay. So this problem can be easily shown that in SNL. The language, the sentence, SNL sentence is something like this one. So we have function C. So this is the function that's paint to give the color, the two colors, say 0, 1, to each vertex, right? And phi 1 and phi 2, that guarantee that the colors are correctly painted. Right? So this is the statement, sentence that characterize two color. So, well, this is just the technical thing, but we just simply correctly define the relational structure and the domain structure, just using the two colors. And the both ends of each edge have to be painted in a different color, and so on, right? So we have the following things, right? If X, so this is the undirected graph, that belongs to two color. If and only if the phi is true on those correctly painted graph, right? So phi syntactically is expressed in two color. But in conclusion, the two color is in SNL. Right? So there's a correspondence between the linear space hypothesis and SNL. So SNL, so this is the SNL omega is the subclass of the SNL. I do not define so what this is in this talk. But you can just take a look at the original paper. So if this one is not computable or solvable in the polynomial time in the sublinear space, so this statement is exactly the same as in SLH. Okay, so now the linear space hypothesis, true or false, that comes down to the logic SNL. Okay, so in this work, I proved that for any decision problem in NL, there is always a correspondence equivalent problem in SNL. So the SNL is covering kind of the most part of the NL. Right? So SNL is pretty much the same as NL if you just consider the log space meaning of the closure. And also SNL is the closed under union and the intersection. So what about the complement? So that's the next topic. Oh, sorry, I forgot this. Complementarity. Okay, two color is equivalent to checking whether the given graph is a bipartite, because you're actually painting black and white, for example. So the complement of two color is called the non-bipartite graph problem. The instance is undirected graph, and then we determine whether the G is not bipartite. Okay, so two color. Well, we have seen that the two color belong to SNL. So what about the other, right? Non-NBG. So this is a complement of two color is also in SNL. So this is actually the SNL statement that guarantee that the NBG is in SNL, right? So a little more complex than before, but this actually shows that the graph is violating the bipartiteness. Okay. All right. So, but the two color is a really easy problem, right? But when we actually we have seen that SNL covers the majority part of the NL, so that it also contains complete problem like a DSD-CON, right? The directed SD connectivity problem. So what about the complement of this NL complete problem, right? DSD-N-CON, so non-connectivity problem. The given directed graph and two vertices, right? We have to determine whether there is no path from S to T in this graph, right? We know that an NL is closed at the complement, so this problem, the complement of DSD-CON, is also in NL, right? So what about DSD-CON? So the DSD-N-CON, this problem is in SNL? I don't know. I could not prove that DSD-N-CON belongs to SNL. Instead, I expanded SNL a little bit to define mu SNL. Well, how to extend the SNL? Very simple. We introduced mu term. The mu term is the term that has this particular form, right? Is the mu operator tells gives the minimum object satisfying this form. Okay, but I do not allow the nested application of the mu operator, right? Something like a mu appeared inside the mu. Just a single application of the mu. And the mu sentence, mu SNL sentence is the extension of the SNL sentence by allowing mu terms, right? And mu SNL is the variant of the SNL using mu SNL sentences. Now the DSD-N-CON, so this is the complement of the DSD-CON, belongs to mu SNL, right? The idea is, well, the use of so-called inductive counting. So, so Immerman proved that NL equals co-NL, then he introduced the technique called the inductive counting in the computational sense, right? Now, I modified the idea and used the logical version of this technique to prove this. Okay, now this is the last topic. Okay, the maximization. As I said, Papa Demetrio and Yannakakis, they talk about the max SNP. So this is an optimization version of SNP. So what about the max version of the SNL, right? So that this is all about the max SNL. So for example, the max 2-sat. So this is actually maximization version of the 2-sat. So this is known to be complete for max SNP, and this one, right? And the polynomial time reduction. Okay. Now we will consider the NL optimization problems. And the Yamakami some time ago introduced the NLO. So this is the NL optimization problems. And we will consider some log space. Well, instead of the polynomial time reduction, we will consider the log space version of the reductions between the two optimization problems. The important thing is, this reduction preserves the approximation ratio with the only multiplicative factor of the fixed constant. Okay. So, so that means that if you have a reduction from A to B, then if the B is solvable in approximately, then the A is solvable approximately. Okay, so this is the reminder of the SNL sentence. So that has this particular form, right? Now we define the max SNL to be the question of asking to find a solution of those things. Those things appeared here, right? And we have to maximize the value of this objective function. The objective function is the total number of those tuples and I and y. Y is actually a series of variables, right? And also s and I, right? That appear here. So we simply counted the numbers in all possible pairs, the tuples. And we try to maximize this number, right? Okay. So the max cut is another problem, it's a maximization problem. Given undirected graph, then we have to find the vertices. For example, if you have a graph like this one, right? We group, we partition into two groups, so that the number of the edges between this group and this group is the cost. We try to maximize this, right? So this is the problem, right? In this particular case, we have the 6 edges in between. So now the max cut is complete for the max S and L under log space reductions. So we can prove this one. And another interesting fact is that the max cut, the same problem is also complete for max S and P under polynomial time reduction. But now, then if you just carefully look at this proof that the polynomial time reduction can be replaced by the log space reduction. That means that the max S and P and the max S and L are pretty much the same. If you just simply ignore the log space reduction, right? So there is no point in thinking about the max S and L, right? Now we have to think about it in a little more weaker version of the max S and L. So Yamakami introduced approximation complexity class, APXL, so approximation log space. So this is a collection of NL optimization problem that can be approximated with constant approximation ratio in polynomial time using log space. So this is the important thing, the log space. So one particular example is the maximum unary knapsack problem given by Steve Cook some time ago. So those are the tuple of the unary numbers, and then we have to find some collection of the subset, and the sum of those numbers have to be maximized, but the number does not exceed b. Okay, so this problem is an APXL, right? Now we generalize the idea of the max UK to define the max tau S and L. Okay, I do not give the precise definition right now because of the time constraint, but the max UK belongs to this one. And also important thing is we can prove that all problem that belong to here is approximable with the constant approximation factor. So that's the most important thing, right? So we have this kind of the inclusion relationship, the max S and P, max S and L, and the max tau S and L. That I do not know how close those things are. So that is one of the open questions. So I just list out 4 questions. For example, whether the max S and L, the max S and P are pretty much the same, but they're exactly the same. So that is one of the questions. What about the tau part, right? Can you get rid of this tau somehow? And what about the complementary problem of an S and L? I introduced a mu S and L, which is an extension of the S and L, to prove the complementarity in some sense. But what about the S and L itself? Is it close and complement? The last one is that max S and L can be approximated with a constant approximation factor. That is not known yet. Okay, thank you very much for listening. And
Do you know if mu SNL is contained in NL?
so you're talking
Seems
about
like it should be, because with the second order universal quantifier and successor, you should be able to define the mu operator, right? No, mu SNL contained in NL.
this one, right?
Yeah, is mu SNL contained in NL?
I think so, because then you only apply it in the mu operator once.
No,
Is
even,
it?
even several times. Because I'm thinking you can define the mu operator if you have a universal second order quantifier and successor. So then you could define the least fixed point of successor.
I see. Yeah, I see. Yeah. Here, so I'm applying the mu operator to the a very simple formula that is not under the scope of the universal quantifiers. So, yeah, of course, then if you apply the mu operator to the very complex formulas, then the computation complexity is actually really blowing up. But here is I try to minimize those things, because then I only try to show that the complement of the DSD-con is expressible within the system. So I do not consider that case.
Maybe you could show that by showing that a greatest fixed point operator is expressible.
Oh, yeah, okay. Well, that's a nice suggestion, yeah.
Yeah.
Okay, all right. Okay, good. Yeah.
Any further questions? Okay, if that's not the case, let's thank our speaker.
I had another question. Can I ask another question?
Yes, maybe while the next speaker is...
What is your conjecture about whether SNL equals NL? What do you think?
Probably not. That seems to be, that chance is slim, I guess.
Yeah.
Because an SNL is very restrictive. So if you use them, if I use them with the closure, like in log space and linear reductions, then well, I can show that all the NL problems are actually included in that closure. But then without thinking about the closure, I do not know how to express there's all possible programming. Can you?
I'm sure not.
Okay, so let's continue
Sorry.
with our second talk of this course.
Hi, I'm staying at Bern, Switzerland. I'm going to attend an international conference which is called WoLLIC 2024. The conference will begin this morning, and I have to give my public talk about my work on logical expressibility of NP. It's a non-deterministic logarithmic space, computable class. And I'm a little bit nervous at this time. Probably, well, because in 30 minutes is the time allocated to my talk, and I have enough slides to cover all the topics, but I'm afraid that maybe I will exceed the allocated time when I try to explain everything in detail. Probably I try, well, the best possible way is to convey the idea as much concise as possible, so that the people understand the framework without really getting into the detail somehow. All right. So my talk will begin at 11 o'clock and probably ends around 11:30 for the 30 minutes allocated time. and hopefully I'll get some exciting questions, so that that helps me improve my work for our journal version. Okay, well, the weather here is, well, it was raining from the last evening, so but it's still raining, and I'm hoping that the rain will stop before I getting out of this hotel. Well, this is an apartment hotel, and I have no trouble carrying my heavy, the bag with the computer and the cameras. Okay, so see you later.